the recording. Okay, I think the audio should be good now. I'm really sorry about that. So here's the thing. When you're doing it at home, you can use Google to figure these out, right? Google, like, where you can use it. Why is this important? And just spend 10, 15 minutes. I don't need you to be perfect. I just want you to be comfortable just being uncomfortable and just asking these questions, right? Because I have not taught you any of these things as of now, right? So you can use it for divisibility, and you can also use it for a basic application you already know about is clock arithmetic, where you do modular arithmetic without even thinking, right? You find two numbers that have the same remainder. That's all modular arithmetic is. I'm going to show you how to do this now. But just because I do doesn't mean you're going to be able to do it. But
you subtract 4 from all those numbers.
Subtract 4 from all those numbers?
Yeah, 34, 27, 102.
How do you subtract 4?
I don't know, just like...
Oh, as a guess? Yeah, oh, because you're minusing by 4.
And then 23 and
then... I don't think that quite works, because let's follow the logic to see why if it's right or not, right? Let's take a look at this example, right? Another way to represent this is 5 times 13 minus 2. Do you agree?
Sure.
Yeah. Oh, 65 is 5 times 13. Yeah. So Nikolai's logic was that, which is a pretty good idea to go down, just logically speaking. He wants to do this minus 4 from all these numbers, and then check whether the new numbers multiplied together is a multiple of 7. Was that your logic?
I guess so. But I'm just not sure.
You're guessing. That's all good. Guesses are very good. Guessing is the only thing we can do at the start. Nothing wrong with guessing. So this is good. Don't think this is a bad thing. And we'll see if that logic holds for a simple example. And if not, that's all good. We can try another guess. So instead, what if, we do the same thing here. We minus 2 from 5, which would be 3. And your argument is that this has the same modularity as this.
Yeah, but just looking at that
33 doesn't, right? 33 is not a multiple of 7, while this is. So unfortunately, that guess didn't work, but that's all good. It's good to explore paths. All right. Okay, I'm going to give you a hint. Think of equivalent modularity. Like, for instance, 17 and 5 have the same modularity when you think of mod 12. Yeah? What's another number, perhaps, that's... Actually, which mod are we working in even to begin with? No.
Like, are we talking basis?
I haven't taught you what mod is, but can you guess?
3. It's not going to be the number because we're... No, base 10.
I'm asking which... not the operation.
Mod 7.
Mod 7.
Because
the number.
Dividing by 7. Right?
Yeah. So think of clocks. It changes every 12, which is like dividing by 12.
Are you saying like since it's like clock arithmetic, it's like 5 and 17, right? Is it like 7 and 34, and then 7 and 27, and 7 and 102?
But 7 is sort of the base, but we're trying to find.
So like.
Yeah.
Is
that we trying? Yeah, you're trying to go down to simple versions. Exactly. So look, 17 and 5 are the same modularity. We think mod 12, which is the number you sort of divide by. Here, we're dividing by 7, so we think mod 7. Does that make sense, first of all? But if we just sort of go intuitively, what's a number 34 is equivalent to mod 7? You can go down a little by little. Same remainder.
7.
7?
Wait, could you repeat the question?
What's a number that has the same remainder or same modularity when you think as 34 when you do mod 7. Now, I haven't even taught you what modularity is, so it's guesses. All guesses allowed here.
So, like, what's the remainder?
I mean, think about this. I'll give you a starting point. It's a very hard question because I haven't even taught you what modularity is. But 5 and 17 are the same modularity mod 12.
Yeah, because like there's a difference between 12 and 5 and 7.
Yeah. So the definition is they have the same remainder when you divide by 12. But a quick observation Niklesh made was the difference is 12. Well, what do you think would be similar to 34 mod 7?
27 and then 20 and then 13 and then 6
And keep going down by sevens.
and then negative 1.
Yeah, you can go -1, but I think we'll stay positive. Makes that calculation easier.
Then you do the same with 27, right? And then it'll go back to 6 again. Right?
Yeah, 27 is also 6, yes.
So 36. And then wouldn't it just go back to 6 as well again with 103?
I don't think it's 6.
Okay, great.
But another way to calculate this would be just do 103 divided by 7 and then remainder. There's 2 ways to do it. You can keep subtracting sevens, but that's hard when the number's
So
big.
14, right?
No, we want the remainder,
Oh, wait.
not the quotient.
98. 5.
Okay, cool. Is everyone following so far? Now I know I haven't taught you this properly, but it's the logic sort of making sense. Yeah.
Then we do 180 minus 4, which doesn't get us.
180 minus 4. Okay, well, we can do that. Yes, 180 minus 4 is 176. But we could do it again if you want. What's 6 times 6?
36.
We can see what 36 is mod 7. What's 36 mod 7? One. If you keep subtracting by sevens, get to 1. Following the logic? Now, I know I don't want you to be able to do it perfectly, but as long as you can follow the logic here, that's all that matters. 1 times 5 minus 4. What's this?
1.
1. Is 1
No.
divisible by 7? So no. This number is not divisible by 7. Do you see how much simpler that is once you understand the logic behind it? Because the computation gets a lot easier. But this is a very powerful property. And actually, the only way you can know for sure is if you get a 0 here in the end. If you get a 0 at the end, that's divisible by 7. If you get 1, 2, 3, 4, 5, 6, that's not divisible by 7.
So if you get 7, it's divisible by?
Yeah, because you can go back down to 0. Yeah. If you get 8, go back down to 1, not divisible. Makes sense?
Basically, you're multiplying 7.
Yeah.
How would we figure out what base it's like?
It's the one. It's the number it's being divided by. Like.
That's a good question. Yes. So I think the simple answer is that the number's been divided by. So it's not. I think you're trying to compare it to bases, and it is sort of like bases, but really all it is asking like what modularity is the remainder when you divide by a particular number. So when you're doing divisibility by 7, you use modulo 7. If I ask you whether this is divisible by 11, you use modularity with 11. You change that with whatever number the question refers to. So we're still in base 10 at all times in this one. We don't go to different bases in this topic. You can think of it, it's quite similar to bases, I would say, but like not exactly the same. Okay, so do you have like a rough big picture idea of why this is useful, right? Now, I don't need you to be able to do all of these things, but as long as the logic makes sense, it's a very good starting point. Now, is there any other questions you have about this? It's good to have questions, so. Okay, now based on what we talked about, okay, I'll ask you this question. Which concept do you think is the most important?
The modular operations.
Modular operations, right? Because it seems like it's useful for a lot of things. And I guess based on that, another question. what do you think is a black swan? A black swan means
the outlier, like the one that's like.
oh yeah, that is like the story. But actually, this is a different term. I just learned it recently.
I thought it was like the things he's the black swan.
No, yeah, of course. I was actually that's probably makes more sense. I don't know why this is called black swan, but what a black swan means is it's something you don't know, but if you did know it, it'll be a game changer in terms of this topic.
Is it the clock arithmetic?
But do you not know that already?
We know that, so it would be mod.
But it changes for everyone. There's no one answer. It's personal opinion.
The things we don't know. So is that like a black swan?
Yeah. So it's definition of a black swan is a thing you don't know, but you think will be super important for the topic if you learn it.
Equivalence class. Oh no, we know.
If you think it's useful, it's unique. It's not one right answer is right. It's whatever you think.
A equals to B mod N.
Oh yeah, I think does that seem foundational to you?
It just seems important.
Yeah, that's all. I don't need you to be sure, but if you feel like it's important, that's good. And I would agree that's a very, very fundamental concept that will help you understand a lot of things. Okay, so
aren't all these key terms important? Otherwise, you wouldn't understand them down there.
well, some are more important than the others. I can't like make it bigger. Like I could have been if I really spent hours doing this, I could have made one have 125. The less important ones have 110. But we don't know that. But just by looking, you just have to get some ideas and then guess what it is. And then when you learn more about it, you might change your opinion, but that's okay. It's good to have assumptions. I'm not asking you to be right here. Does anyone have any other things they think are important?
Mod, because that's like before you even get to like mod N or stuff, you need to know what mod is.
Yeah, fair. I agree. Yeah, good. So that's like the biggest possible topic. What else in your all these answers have been correct so far, but I want you to guess what you think is important for you personally. And there's no right answer, wrong answer. We're all just guessing here. Any other guesses? Negative modular. Yeah, that's a very, very interesting topic. We'll get to it a bit later because it is a bit unusual because you won't like you don't know like when you modular is defined with divisibility, and you really only work with divisibility of positives. But negative modular sort of allows you to think of divisibility for negatives even. So it's a very powerful topic, but we will get to it soon. But I think, are you curious about that? How it works? Yeah, that's also a good thing to be curious about particular topics.
What's your one?
I mean, my one's not going to be the most fair because I've already done this, but
okay, then think you haven't done
it. I think the most useful would be the operations, in my opinion. Once you learn modular addition, subtraction, multiplication, exponentiation, and you learn how to use them, it's very powerful for making a lot of problems simpler. But that is having all this experience. So it's not really like I'm learning anything new. But the reason I'm asking you this question is having these things you're curious about is super powerful for understanding it. And like when you're at home, if you feel like you're curious about any of these things, research them a little, right? And I think, yeah, negative modular is very interesting. I was actually researching it a bit yesterday because I actually forgot what it meant. And it's quite interesting, like what they talk about. So it's a very powerful topic. But we're going to actually go back to normal class now. Okay. So we're going to start with what modulo means. Or modulo / modulus, modular arithmetic. Okay. Before that, actually, where do you think in real life, other than clock arithmetic and divisibility, what real life problems do you think use modular arithmetic? Any guesses?
Does it have something to do with science?
I might. I'm actually not sure about that. That's a good question. I should look into that. I think it might. Yeah, probably good. The one I was thinking of was like, actually, here's the thing. If you have any number theory topic, which is like divisibility factors, that sort of thing, there's usually an application in computer science somewhere. As in, like, your passwords and stuff, they're usually stored with like this thing called a hash function, and that uses modular arithmetic. So modular arithmetic is very useful for storing cryptography, like when you're trying to make something cryptic, like Bitcoin. That uses these ideas. Bitcoin has a lot of modular arithmetic, right? Now, actually, exactly how, I'm actually not sure either. I'll actually look into that and I'll get you to, I'll talk about it next week. But I haven't actually looked into that too much either. But I know a little bit of it, but I don't know that much. So I guess, yeah, so like these aren't just really abstract concepts that are completely useless. I'm trying to say is maths, when it's even when it seems abstract, ends up popping up somewhere. Like you're gonna learn actually, like maybe in 2 months or so, you're gonna learn about maybe imaginary numbers. Imaginary numbers, right? That's the name. But
it's imaginary, so you don't need it.
So I genuinely thought it was useless. I just thought it was someone coming up with it for fun, and that's what they did. They did come up with it for fun, but it comes up in quantum physics, which is like what everything's built on now, right? So, like, maths is weird in the sense that all these things that seem so random and abstract end up having a use at some point. So that maybe the maths research that like the best maths professors do right now, they might be useless right now, maybe in 50 to 100 years time, maybe some like new program or whatever needs it, right? Or new field needs it. So that's how powerful maths is. So don't just think of these as random things you're gonna learn. They actually come in very handy, and like even if you don't end up doing these things, having an appreciation of them is useful. So key idea, A is equals B modulo N. Another way to say is A is congruent to B modulo N. Okay, this is just equivalent. They're just definitions, right? If A is B modulo N, it just means A is congruent to B modulo N. That's another way to say it. But what do you think both of these terms mean? This is the way to this is the algebraic way to represent it. This is the
A is the same to B modulo, which is modulo N. So if A equals B, that means it's modulo N. Because doesn't congruent mean same shape or something?
That's actually that's in geometry. Congruent here is a different congruence. Maths has like a lot of
that's too many.
good connection though, but it's all, I think it's good to make that connection because congruent means same, and what it's saying is these are the same. And I know this notation looks weird. Okay, I'm sorry.
What?
That's not. I did that in like year 9, and then I changed it to normal name, and then he changed it back. He was like, no. It's because he's going gym right now, and I'm not going, obviously. Okay. And first of all, this notation looks weird, but what it actually means is A modulo n equals B modulo n. So think of it more like this. It's saying both of these numbers modulo n are the same. But mathematicians are lazy. They just put one of these things. They were like, let's get rid of this one. But so think of it as operating this way. So we're saying if we do modulo n to A and if we do modulo n to B, they're the same thing. Cool. But what does it mean? Like, what is it meaning? What does it mean that's useful for us? What's the definition of this? In terms of concepts we already know.
Okay, so A equals B.
So you're saying A has to be the same number as B?
I mean, I guess so.
That's a good guess. And yes, this is partially everything. So if 2 is equal to 2 mod 5.
Or something.
This is what do you mean same formula?
I don't know, they have to have something which is the same, right? Because it says concrete.
Yeah, something is the same for sure. So I think your definition is a bit too strong. You're saying that the two numbers have to be equal, but that's just normal equal. That's just normal, like you're saying 3 is 3, yes. But what does congruent mean in this context? What is the same? Guess. I mean, what we talked about. All these, we had this.
I mean, you wrote A modulo n equals B modulo n, so modulo n has to be the congruent.
I mean, but there is a concept already that you can apply this to. Divisibility, yes, close, very close. We saw before that 17 equals 5 when you do mod 12, clock arithmetic. So this is why your definition is too strong, right? If you have just equal, 17 and 5 aren't equal, but they are the same mod 12. Why do you think? What definition do you think makes sense here?
Your one.
Which is?
The clock arithmetic.
I mean, I'm not saying this is just an example. This is not a definition. Based on this example, what definition do you think makes sense? I haven't come up with a definition yet.
The second one.
I mean, they're both correct.
What?
These are both right.
Said that one was too strong.
But this is correct as well. But I'm saying just this alone isn't enough. These are both true is the point. So what definition would satisfy both of these examples?
The second one would satisfy both of them.
But what is the second one? I haven't said a second one.
The second one, 17 mod 5, mod 12.
Yeah, I agree with that. But I'm saying this is also true. Both are true. Both are correct.
Yeah.
These are both statements that are correct. What definition can you guess would satisfy, like, make both these correct? Like, think about your definition, right? You said before that they have to be equal. If that is the case, well, yeah, this is true. But this will be false, right? Agree? Because 17 is not 5. But what's another definition we can think of? Based on, like, the problems we talked about. What are the concepts we've talked about so far with, this example, for instance?
The divisibility, like 2 divided by 2 is equal by 1. And like the remainder.
Remainder. That's the idea. That's all it is. That's the definition. The definition of this is two numbers are congruent if A and B have the same remainder. When you divide by
by mod A or B, by a specific mod.
The modulus given though.
Oh, by mod n.
Yeah, by n. So A is equal to B modulo n means A and B have the same remainder when you divide by n.
Oh, so that's like A and that's B.
This is A, this is B, this is A, this is B.
Oh, I thought like one was A and two was B.
Oh, no, yeah. So the statement has both numbers.
Okay.
Sorry.
I thought that was like.
Yeah, that's all. There's a clarification you make when you learn about this, right? Like, I can't anticipate that, so it's good to just have those doubts and just fix them over time. So, does that make sense? And that makes sense with a lot of the concepts we've talked about so far, right? Now, this is a very powerful thing. So that definition makes sense, all right? But okay, we're going to talk about a property of this. So we know it means the same remainder, but if you come back here, we used a trick for remainder, which was instead of just dividing and finding the remainder, we could just subtract multiples of like n, which is 7 here, from a number. So for 34, you could keep subtracting 7s to get a number with the same remainder. Why do you think we can do that?
Because it's in mod 7.
Yes. So yeah, like we can, yes, agree. So that's the fundamental thing. If it's mod 7, you do subtract by 7s. If it's mod 11, you'd subtract by 11. So if it's mod n, you'd subtract by n. Yeah, so that's a key pattern to observe. Very good. But why do you think that pattern exists?
Because if you use a different number, it won't get you the same answer.
But like, why do you think this is true? Well, what's like the proof for this? I'm gonna give you a quick proof just so that I want to make you familiar.
Like it's already A to B mod n, so you already know that it's like the remainder.
Let's say A is B mod n, right? And let's say that if you broke this down completely, if you like keep subtracting n's, the smallest possible n is A is 2 mod n. That would mean B is also 2 mod n, right? What does this tell us about A and B? It means A has a remainder of 2 when you divide by n. So that means A is some whole number times by n plus 2. Agreed? K is some number we don't know, but we know K is a whole number. What this says, K is an element of an integer, the set of integers. K is an integer. That's all it's saying. It's similar. You don't need to, I'm just making you familiar with this notation. It's okay if it doesn't make sense. What's somewhere we can write B then?
B K equals Kn plus 2. So
if you have K, that means it's equal to A. B is any number that has a remainder.
Okay, then Cn plus 2.
Yeah, any letter. Cn plus 2 would work. Ln plus 2 would work. As long as it's different from K. Because we want this to work in general. C is also a whole number. Yeah, makes sense? And basically, well, you have... What we want to do is show that to go from A to B, we can subtract what? Or subtract or add a multiple of
2. N.
N. So some multiple of n, we can go from A to B by adding or subtracting some multiple of n. Makes sense? That's sort of logic we had used here, right? We multiplied 4 times 7. Sorry, we subtracted 4 times 7 to get to 6 from 34. Wait, does this first of all make sense? Oops, wrong color. 34 equals 6 mod 7. This is the jump we made in the example before.
Oh, this is mod n, right?
Yeah.
Okay.
We're just generalizing this.
Yeah.
So look, 34 is 6 mod 7 because when you divide 34 by 7, the remainder is 6. And when you divide 6 by 7, the remainder is also
6 by 7.
Divide 6 by 7. 6, yeah. 0 remainder 6. Makes sense? We're just trying to generalize this property to show why it works. But the key observation we made was you could just make 4 jumps of 7. You can subtract 7 by 7 times 4. But the point is that it's a multiple of 7, right? So we're trying to see if this is true in general, which means we're trying to prove that we need some number times by n, some whole number. Let's call it not a. Let's go p. Makes sense? Some whole number times by n to go from a to b. Agreed? That's what we're trying to prove. Now, this is a representation of a and b algebraically based on this modularity here. And then what we can do is we can go, this is sort of the remainder. Let's say 2 is a remainder, right? If we go a minus b, what do we get? No, we like, yes. Not quite. We just literally just subtracting these algebraically. We have a and b in terms of like n and some whole number.
Okay, so it's just k.
Is it kc? You do kn plus 2 minus.
No, it doesn't. Don't. When you're subtracting that, doesn't that n and plus 2 get cancelled?
Oh, this is c times n. These cancel, I agree. But these don't exactly cancel. It's like you have 5n minus 3n. Does the n's cancel?
Which way do you want to put it? CK or KC?
It's neither.
CK n squared.
We're subtracting, we're not multiplying.
Isn't it just CK?
Yep, 2 minus 2, they cancel. Yeah. But then we still get kn minus cn. What do you do with this?
I mean, there's one variable that's the same.
So you can, what can you do with it?
Get rid of it.
Not quite. It's like, think about this. If you had 5n minus 3n, would you just get rid of the n's?
No.
And just do 2?
Oh,
you can't do the same logic.
You can just subtract those, right?
You can subtract the coefficients.
So that would just... What is k minus c?
Okay, I know it seems pointless, but you'll see the point of it very soon.
Like, you can't minus k minus c. You just do whatever k minus c is, and...
That's all you can do. I agree. I know it seems pointless for you right now, but look, here's the power. Look, what are we trying to prove? That it's some whole number times by n is the difference, right? To go from a to b. Go back to what we're trying to prove. Make sense? If you're confused, let me know. I can clarify a bit. Like, think about this example. Compare back to this example. We made an observation here. We're trying to generalize the observation for any n instead of just 7. We showed that 34 to 6, you subtract by 7 times 4, which was the whole number. Now we're trying to show that a to b, we subtract by some random number multiplied by n. Yeah, and we don't need to know what those numbers are, but we just need to know that p is a whole number. Here's the thing. A minus b is n times this number. And we know k is a whole number. We know c is a whole number. That means k minus c is that still a whole number or no? Yeah, it is still an integer. If you subtract 2 integers, you get an integer. So this is a whole number times by n.
Okay, so...
That means to go from a to b, you subtract by a multiple of n. This is a multiple of n. And that's your proof done. Does this make sense?
That didn't make sense.
So look, I did a minus b, right?
Yeah.
That's the difference between a and b. That's like the difference between 34 and 6 is 28, right? You can just do 34 minus 6 to get that difference. Do you agree that subtraction just gets the difference? And what I've shown is that when you subtract them, you get a number that's n times a whole number. N times a whole number is a multiple of n. Make sense?
Yeah.
So the difference is a multiple of n. That's exactly what we tried to prove at the start. Thing is, I wanted to prove this. I didn't know this before. Now I've done it by showing that when you subtract them, you get a multiple of n. Because it's n times some whole number. And this is a bit more of an advanced proof. but try to understand the logic behind it.
So, can you go up for like?
Actually, which part would be confusing for you here?
I don't understand where the K came from, and like that K and then the Z.
K just symbolizes the number it's just like a positive number.
So that's a good question. Where did K come from? We don't know, but what we do know is that like this is the definition, right? Since A is 2 mod n, the remainder is 2. If the remainder is 2, that means A is some multiple of like n plus 2. Do you agree with that definition? We don't know what K is, but K times n is some multiple of n, right? It's like if a number remainders, think of all the numbers that are 2 mod 7. You have 2, 9, 16, 23, 30, right? 2 is 0 times 7 plus 2. 9 is 1 times 7 plus 2. 16 is 2 times 7 plus 2. Makes sense logically? And then, so any number mod 2 mod 7 is like some number times 7 plus 2. That's what we've done here. We don't know what that number is, but we know it exists because it is a remainder of 2. Does that make sense?
Yeah.
That's, yep.
What does that like mean?
Also, this means element of. K is an element of Z, and Z is a set of integers. So K is an integer. It's all the same. Makes sense? Because, it's not like if I had, it doesn't make sense for this number to be like 1.5 times 7 plus 2. That's not even a whole number. How can that be a multiple of that? How can that be 2 mod 7? It only makes sense when the number you're multiplying by is a whole number. So I'm saying A is K times n plus 2. And I know for a fact that K is K is an integer. That's why I've labeled it like this. Does that make sense to everyone? That was a very good question. These are questions to clarify. Anyone else? Even if you have the slightest doubts, very good to ask these questions. Any other questions? Okay. Okay, now does the proof make sense here? All I have is 2 numbers. K minus C is a whole number times by n. It's a whole number times by n. It's a multiple of n. So the difference is a multiple of n. That's where the logic comes from. So that's the proof behind the trick you can use. The trick now that you can use is you have 2 ways to check congruence. First way is what? What's the 2 ways actually? What are the 2 ways to check congruence?
Finding the remainder.
Yeah, directly, which is use the definition. You divide both numbers, find the remainder. If they are the same, they are congruent. What's the other method now that we learned about this proof?
So, like just subtracting whatever A and B is, right? Then just getting that whole thing, just like K minus C.
I mean, this is a proof. You're not going to use this proof exactly yet.
I have a question. For K, is it like an unknown number, or does it stand for like a number?
It's an unknown number, but we know it's a whole number because of the fact that it is a remainder of 2. Does that make sense? It's just something we don't know, but we know it's an integer because of that property. And that's how proofs are in general. And like it is uncomfortable at the start, but I'll slowly incorporate little by little proofs in the lesson so that you get used to them and understand how we form them, because they are like the backbone of maths at the end of the day. So back to your point. So we can use the ideas from this proof. If you were to simplify the idea down into a couple of words, is there a way to represent this simply? How we can check congruence?
17 minus 5 equals 12.
What's the more general way to say it?
You're just basically doing it directly.
Directly is literally dividing. Oh, sorry. Definition of direct would be divide both numbers by like n. and check if the remainder is equal. So the direct method for like 17 mod 12 wouldn't be subtracting 12. It's doing 17 divided by 12. Yeah, and 5 divided by 12. When you do 17 divided by 12, you get 1. So the remainder is 5. 5 divided by 12, it's 0. So it's remainder is 5. Then you say, oh, these have the same remainder. Therefore, they must be the same modularity. They're congruent modular 12. But what's the shortcut? Difference. That's the key term. Difference is what? What about the difference?
It will give you like the modular and the mod, right? The difference between A and B will give you the mod, right?
Not exactly. It's something close to that.
The difference between both of the numbers, between n, the beta side, and then
Is it like
Let's say the mod is n. Assume mod n for now. What do we know about the difference between the two numbers?
it's a whole number, and it's a multiple.
That's the key thing. The multiple of n, not just n. So 17 minus 12, 5 is 12. But 29 minus 5 is 24. They're still both congruent mod 12. But they're not 12 is the difference. It's a multiple of 12. Clear? So the difference is a multiple of n. That's the key observation to make. So this proof wasn't just useless. It is very useful for finding modularity. Right? It wasn't just me giving you a cool maths proof. And that is part of it, to show you, to be comfortable with understanding how maths works with proofs. But now we have 2 ways to check congruence. Okay. So you're going to use both. I'm going to ask you. I'll give you a list of numbers. And then I want you to group them based on, like, put all the numbers in the same group in one list. There's going to be 3 groups here. We're working in mod 7. Let's do 9 actually. Mod 9. I'm going to give you a list of 10 numbers. Okay, yeah. 1, 3, 7, 91, 48, 88, 73, what else? 70, 28, and 57. There's 3 groups here.
91 is one of them, right?
What's that, sorry?
Is 91 one?
Well, I'm trying to say, like, there's 3 groups. Like, all of the things in the first group will be congruent to each other. All the things in the second group will be congruent to each other. All of the things in the third group will be congruent to each other. Can you identify the 3 groups? Is the question.
73 and 70. It's just going up at 2.
What is congruent mean?
It means
So they all have the same remainder.
the same remainder when you divide by 9, because we're working in mod 9.
There's 2.
It's best starting point. Just find any 2 numbers that are congruent. That's a good starting. You need to find if for any number to form the group, you need to find at least another number that it's congruent with.
2, 1, 2, 7. Oh wait, no.
There's 10 numbers.
How can there be 3 groups? Should I go to 12?
What do you mean?
Like how many? Is it meant to be uneven groups?
Yeah, it's not. They don't have the same number of. It's 4, 3, 3. By the way, the split. There's 4 in the first group, 3 in the second. Or
is the first one 1, 3, 7?
Are they the same group?
Yeah.
What does same group mean?
Because like when you divide it by 9, it's just gonna be 0, 0, 0, and then you make it.
But we want remainder, not the actual quotient. This 1 and 3 have the same remainder when you divide by 9.
Yeah.
Same remainder. I think you're confusing quotient and remainder. Remainder is the number left over. 1 divided by 9 is 0 remainder, 1. 3 divided by 9 would be 0 remainder, 3. Does that make sense? So you just need to find the remainder. That's it's good, just makes sense. Yeah. So I'm gonna give you guys some time. So if they're in the same group, they are congruent. Is the thing. Create. So the question would, like, if I put it in words, would be create 3 congruent groups. I would agree that is, they're all in the same group. Okay, I'm going to give this a starting point, and I want the rest of you to figure out from here. This is a very good start.
Then cross out like 173.
This is a complete group. So Louise just actually found a group for you guys. I want you to find the other 2 alone. Do you understand why they're in the same group? First of all, if you're confused, try to understand why that is. And then after that, try to find the other groups and justify it to yourself. You know, the answer isn't enough. It's that you understand how these groups are formed. Why are they the same group? They're all in the same group. Why? Can anyone tell me the answer? Which is
1.
1. If you do 73 divided by 9,
It's 1.
1. Another thing you can also, what's another way to check they're congruent?
You can just find the
Difference. 73 minus 1 is 72. Divisibility check plus 9 is?
Pardon?
What's a divisibility check for 9?
It's the remainder one.
No. Like, what's a way to check if a number is divisible by 9? Like a quick check.
0, the multiples are 9.
Yeah. There's like a trick for this. Yep, add the digit sum. And if that is divisible by 9, then the numbers, it is. Yeah. So you can quickly check the difference as well. That's why 1 and 3 aren't the same modulus, because the difference is 2. 2 is not divisible by 9. Try to form the other groups. And actually, I would call this the 1 group, because 1's like the fundamental thing. It's like the remainder, right?
So 3, 48, and 57.
I want everyone to try to construct it fully.
And then it's
Yeah. What are actually the names of the other groups? What are the 2 other groups? What's like the fundamental remainder for the other 2 groups? 3 and 7, right? Does that make sense? By the way, does anyone have any questions about this? You can be honest, like, I want you to ask questions here, right? If you have any doubts, if you feel like you don't know how to get there, let me know, right? Because then we can. So I think it's clear to see that these 2 are other 2 groups, right? And if you check, yeah, so 3 is in the group 3. What's another number that's 3 mod 9? Congruent to 3 mod. If someone else, very good, Niklesh. What's another number? And why is that? Exactly. That's one way to check. Just do the division. Remainder is 3. What's another way to check?
The difference.
Difference. Yep. And the difference is 57, sorry. The third number. Yep. 45 would be correct for 3 and 48. Yes.
Isn't it just 9?
Oh, yeah, you can do this one too. These 2. You can compare any 2. And once they're in the same group, you can compare. So 48 to 57 is just 9. Easy, check. Yeah, makes sense. Okay, and then the last group would therefore be 7, 88, and 70. Does the logic behind this make sense to everyone? Cool. That's the basic concept. That's congruence. Quick summary for congruence. Congruence. What's the definition of congruence? Can someone who hasn't answered as many questions today tell me? Give it a guess. What's the definition of congruence? What does A congruent to B mod N mean? Distribution.
Two numbers with the same remainder.
Yep. And if it's mod N, it's same remainder when you divide by N. Exactly. Well done. Definition is two numbers with the same remainder when you divide by N. What are the two ways to check for congruence?
Just directly or
yeah. And directly would be what? What do you do directly? I'm going to hide it.
Use 100% of the brain.
It's fine to make a mistake here. You're trying to recall and you might not get it right. That's fine. Sure. We'll do a couple of questions of practice afterwards, right? It's important. If you can ever not sure, just let me know, okay? And that's perfectly fine. I'm happy to explain. Indicate a hand up. You've answered a lot of questions, so I'll give it her first preference. Yeah, directly, yep.
When you divide the two numbers by n and then check if they have the same remainder.
Yeah. So does that make sense, Kushal? You literally do the division. The definition means they have the same remainder. So like if you want to check if like 42 and 8 are congruent mod 5, you do the division. You do 42 divided by 5. What's the remainder when you do that? 2, right? So you get 8 and then minus 40 is 2, right? And then if you do 8 divided by 5, yeah, 1 remainder 3. That means are they congruent or no? Not quite. You check these two numbers. Check if the remainder is the same. If they're different, they're not congruent. They're only congruent if the remainder is the same. Does that make sense? So what would be a number that's congruent to 42 mod 5? We need 7. Yeah, exactly. We need a number with a remainder of 2, 7. So another would be 2. 7 also works. 12. All these numbers. Does that make sense? Very good. So it's good to clarify these early. And Niklesh, do you want to explain the difference method? If you want to.
No thanks.
No thanks. Who wants to explain the difference method? To compute, to check congruence. All of you guys don't want, that's okay. I'm happy with all of you participating, so I'll go give that explanation. Two numbers are congruent. Sorry, the second way to check congruence is to check if the difference of the two numbers is a multiple of n. So as an example, if you do 42 minus 8, what's the difference?
42 divided by
42 minus 8. Like if you want to check if 42 and 8 are congruent mod 5.
74.
Yeah, 34 is the difference. Is that a multiple of 5?
No.
No. Therefore, they're not congruent.
So you just check if it's a multiple of n.
The difference.
Yeah, so you check if the difference.
Exactly. Yeah. Cool. Those are the two checks. And the proof for that is here. Proof for that is here. You don't need to know the proof. It's just good that I just wanted you to see a proof in the first place, to get more familiar with seeing proofs. And then maybe later on, we can start constructing our proofs on our own as well. But that is a skill for later, for sure. Okay, we've done with basic congruence. Now let's get to the thing that you said was super important. Do you remember who said that operations are important other than me? I remember one person said that. I think it was a Uniclash. When I asked for the most important concept, You thought. You said congruence. And we covered that. We're actually going to cover the other one, which is going to be
modular.
No, that's the topic. Like
That's-
he's talking about the addition, subtraction.
I know. I'm talking about. I forgot the name.
for the name.
Oh, my bad.
Oh, yeah. I mean, yeah, it is arithmetic in the modular. But that's also a topic name, but it's also like the arithmetic operations of modular addition, modular subtraction, modular multiplication. And I don't think you do division. No, you don't. We do modular exponentiation, though. That's powers. So now let's get to the fun bit, which is operations. And that's actually when we can solve the problem we talked about here. Do you remember the divisibility problem? We'll be able to solve it once we learn about this. Okay, now here's the operation slash, another way to think about it is algebraic properties. So the first property is, it says, actually, let's say, we know that A is equal to B mod N. Cool. And we also know that C is equal to D mod N. These are known facts. Assume these are known. And then what this says is A plus C equals B plus C mod N. That's the first property. The first property is that A plus C equals B plus C mod N. Can you come up with an example for this? Just realized I haven't gone a break. We'll do this, cover this quickly, and then
I mean, if we take a break, it's just the end of class. We might as well play Kahoot.
in the break. Oh no, you want to soon finish this, play the Kahoot?
Yeah. Just
Okay.
Like
All right, cool. Let's do that. Sounds good. We'll go another 10 minutes, then do Kahoot. Yeah, sure, go for it.
Well, you already know that A equals B is like already mod N.
Yeah,
And
that's
C equals C is just the same number. So
Yeah,
that yeah.
but I guess this makes sense intuitively. But we're dealing with a new thing here, right? We're saying the remainder of A plus C is the remainder of B plus C when it's mod N.
Okay, then it's just like it's the same thing. It's like 17 and what was it, 5, right? Yeah, it's just like that. It's like just bigger numbers there. So not like it could be like 12 plus 5 and then
Oh, yes, that's a good example.
Could get you like just 3 and 2, which would be 5. So 17 equals 5. Oh wait, no.
But 3 and 2 aren't mod.
Yeah,
You need to
sorry.
find two numbers that
Yeah.
are congruent to each other. No, but you're on the right track. Very good example. We can deconstruct. Do you remember the example 17 equals 5 mod 12? Yes. We can actually deconstruct this into something that looks like this. You said 12,
12 and 5. Or is it
12 and 5, yeah.
But they're the same thing, they're just like
So this is like a C. 5's like the C, right?
so 5.
Well, what's A and B then?
B has to be 0.
0. Yeah, B has to be 0. Is 0 congruent to 12 mod 12? Yeah. 12 remainder when you divide 12 by 12 is 0. That means we already know that 0 equals 12 mod 12. Do you see how this holds then? 12 and 0 is like the A and B, and then 5 is our C. The reason this is handy is because, actually, let's come up with an example where this is handy. Because actually, this property is less powerful than the multiplication property, which is the one that's really going to come in handy. Like, do you remember the multiplication one we saw here? Which is like, No, we did use this here. I'll tell you why. No, actually, it's not as clear. Give me a second. I'm trying to come up with an application because the super powerful one is the multiplication one when we get to it, but I'm trying to find an application for this one. I'll give you a question for that. But in the meantime, I'm going to give you the more general property, which is A plus C is congruent to B plus D mod N. Make sense? Because look, A is the same as B, C is the same as D. So what we're saying is we preserve the remainder when you add things. So what do you think is a good example of this? What do we think is a good example of this?
For that. Oh wait, this no. Oh,
We need, yeah, completely different numbers.
Okay, then. So
I'll give you an example.
So we can do the same, like 12 and 5 with A and C, right? And then, but then it still has to equal 5, and we can't do 2 and 3, right?
Yeah, you have to find a number that's congruent to 0 and like. I mean, you can say C is D and then do 5 and 5, but that's kind of cheating. I'll give you a question actually that will make this property clear. 34 plus 17
Okay, 10 and 12.
mod 11.
Oh, okay.
Now I know you can add these straight away, but is there a different way to do this without adding 34 and 17 ever?
Wait, repeat.
So I want you to solve this without ever adding 34 and 17. You're not allowed to do that.
You add numbers outside of that?
Yes, you're allowed to add smaller numbers. I know I'm like restricting you, but I want you to.
Like small numbers. I just thought, okay, I'm like 20 and 40. What if you just divide it by 17? Isn't that just
But we're in mod 11. 17 dividing by like any other thing outside the mod kind of like removes a lot of the properties. We're in mod 11, by the way.
Okay, so without like breaking it down, right?
You can break it down. I just said, yeah, of course.
Wait.
You can't add 34 and 17. So you can't like,
Oh,
I don't want you to add them together and
Yeah,
then.
so you just do like 20 and 14 or something, and then like 12 and 5. Oh, wait, we're in mod 11.
Mod 11. What's the number 34 is congruent to mod 11?
33. It's close, so it's like 34 minus 33 is 1.
And 6.
Yeah.
1 and 6, yes.
Yeah.
1 and 6. 34 is congruent to 1. Makes sense. The remainder is 1. 17 is congruent to 6, like Michelle said. Which is 7. So it's equivalent to 7 mod 11. If you add these two directly, you'll get 51. And that's also 7 mod 11. But we could do it even without adding them together.
Would this be faster?
I mean, you could just divide it by
This is faster when the two numbers are like maybe hard to add. Then you might do it easier here. Okay?
Yeah.
Or if you know, like, let's say this number was 33 actually. Then you know this is 0. So you can immediately make this 0 and just have this number is the whole thing. But I just want you to use the property. But this, like, there will be applications at some point. So I want you to use the property for now. Now, do you see where the property is used here?
Wait, can you divide even if you're in a specific mod?
What do you mean divide?
Because you said if you had 34 and 17, it will equal 54, right? Can't you just divide by 8?
Divide by 8.
Wouldn't that just keep? Oh no, that's 56.
Oh, but we like, you don't want to divide by a different number because like we're in mod 11.
Yeah.
We only care about the remainder when you divide by 11. the remainder. And when that happens, when you divide by 8, a lot of the properties are sort of gone. But do you see the examples of this? What's like the A, B, and the C, D here when you use this property?
A, B, what's it about 1050?
Yeah, we're going to do Kahoot after this. What's the A? What's the B? What's the C? What's the D?
A number.
In this example.
Oh.
G space.
I mean,
No.
we really have to worry about what A,
Well,
C, and D, and D are even after we solved it.
well, it's good to understand how we're using the property.
So, like, I really get what we did.
Or from like which step, here to here? Well, I just found a number 34 is congruent to mod 11, which is 1.
It's 20. What's like the whole idea?
The idea is that you can find another number that is congruent to and replace it with in the equation.
Can it be like 11 and 23? Or A and C?
For A and C,
23.
I think, well, A and C are 34 and 17, right? That's given. That's like the first two numbers.
Oh, okay. Then what's B and D?
1 and 6.
Yeah, B and D are 1 and 6. So what we
Oh,
did
yeah.
was we replaced A with a number that's equivalent to it in mod 11, which is 1. That's when we said A is equal to B mod N. Yeah. And then similarly, we did replace C by another number that's congruent to it, mod N, mod 11.
So like they're both the same.
Yeah. 34 is equal 1. 17 is equal to 6 if you just do the remainder. You can do congruence with either of the two methods we talked about before. Make sense? And then we replace C with, I don't like purple. Need to get rid of that. C with D, which is 6. We replace it with simpler versions because that will make it easier to compute. But there's no rule that says it has to be simpler. You know, we could have gone 34 plus 17 is 45 plus 28. I just added 11 to both. They're still congruent, right? But why do we do that? That we're just making life harder. It's better to just replace it with the easier version. Make sense? So we can use this property in a way that's convenient to us. That's the, yep.
What's the answer? Like another.
Well, 1 plus 6 is just 7 mod 11.
But what does that mean?
That means these two numbers added together has a remainder of 7. You divide by 11. Makes sense? Because they're congruent, they have the same remainder. Yep. Good question. These are good to understand what like the implication of it. Yeah, exactly. So is that clear? And you can check if you want 34 plus 17. Like literally do the addition and check if the remainder is 7. And it will preserve. We just have shortcuts now to reach that same outcome. Cool. We'll wrap it up there. And next week we'll get to the more cool operations, which I think multiplication and exponentiation. Very powerful. Like you'll be able to figure out what 2 to the power of 100 is mod 3. Any guesses what 2 to the power of 100 is mod 3? Calculator probably can't do it. Probably it's too big. It's such a huge number. Can't even do it. 2 to the power of, oh, it doesn't have powers. Let's see if 2 to the power of. Do you think you can calculate it?
You've already done it. Okay.
Okay, what if I ask you 2 to the power of 10,000 mod 3?
Why do you put 100 though?
Because I'm trying to show that it's so powerful. You don't even need to know what the number is.
3, 6. Wait, no, that's just.
It's negative 1, 1, negative 1, 1. Oh, it's 1.
So that whole thing in mod 3 is just 1. That's stupid.
It's a remainder. The remainder is either 0, 1, or 2.
Let's see if I can type that.
Can you do 2 to the 10,000? Overflow. You can't do it. It's too big. But I can solve the fact to find a modularity. That's why modular arithmetic is powerful. And we'll get to the cool stuff next week. So you'll be able to know the modularity. Like, you know that the remainder when you divide this by 3 is 1, even though you have no idea what the number is.
2676506 times 10 to the power 30.
That's an approximation
That's why.
because it's too big. That means it's got 30 digits, 31 digits. 10 to the 30 is what it means. And 2 to the 10,000 is like probably hundreds of digits. So big.
Whoever made maths was an overthinker.
It was made over hundreds of years. Yeah, we'll wrap it up there. Let's do a quick Kahoot. Any final questions? Well done today. Yeah, so I'll send the homework. It'll be basic, just finding congruence, maybe some addition properties questions. And then next week we'll get to the fun stuff.
I have one question though.
Yeah.
Did you stop recording, by the way?
No, I haven't.
Okay, I suggest you stop recording.
Okay. That scares me a little bit.